Hi, my name is Puriya and today we are going to make carbon quantum dots as a novel fluorescence nanomaterials and we will use them as a biosensor. But first, let's have an orange juice. Oh wait, I can't drink this one in the lab, but I can extract ascorbic acid out of the orange juice and use it for making carbon quantum dots. Here I have laid out all of the supplies we need for today. Most importantly, we need a hydrothermal autoclave as we will be using a hydrothermal synthesis method to make our carbon quantum dots today. I have opened the hydrothermal autoclave for us here. This inner Teflon reactor is where we will be placing all the powdered ingredients and water. We need 2 disposable plastic weighing trays and plastic scoops to weigh out our powder ingredients. This powder ingredients is ascorbic acid, which we have extracted them from the orange juice I was drinking in the beginning of the day. We also need a glass pipette and pipette controller and a glass beaker. We will be using a 0.22 micrometer filter and 10 milliliter syringe to filter our sample into this plastic flask. Firstly, I weigh 1 gram of ascorbic acid powder. Using the scoop, I add the ingredients until I can see a number as close to 1 gram as I can get on the screen. Now that I have finished weighing the ingredient, I transfer it to the beaker carefully. I will open the glass pipette packaging at the tip and insert that into the base of the pipette controller. Now I remove the packaging and go ahead and suck up 25 milliliter of deionized water. I dispense that into the beaker that has our powder. This pipette glass is 25 milliliter, but we need 50 milliliter, so we need to do it 2 times. Using deionized water is important because we don't want any unwanted ions such as magnesium, which can be found in tap water, incorporating into our carbon dots. These ions would change the properties of the carbon dots and we don't want that happening unintentionally. Now I'm going to put this beaker on top of the plate and start stirring. I set the stirrer to 300 RPM and make sure the heat setting is off. Now we can see that the magnetic stirrer is spinning. We'll just leave it for 15 minutes until it mixes and we no longer see powder particles. I will now use the strong magnet to pull the magnetic stirrer out. It prevents you from having to fish for a magnetic stirrer yourself with dirty gloves, causing contamination. The homogeneity of the mixture is very important as we want to make sure all the ascorbic acid powder has properly dissolved in DI water. In other words, we want a perfect degree of the homogeneity or mixture quality, which means ingredients appear in the same proportions in any sample taken at any point of the mixture. This will help us to have a more even reaction during the synthesis section. In this case, I use vortex to stir the solution more strongly. I will transfer the solution to a Teflon flask and transfer it into the hydrothermal autoclave reactor. Hydrothermal synthesis method is a low-cost, environmentally friendly, and non-toxic route to produce novel carbon-based materials from various precursors. Typically, the hydrothermal autoclave Teflon reactor used to carry hydrothermal reaction at high pressure and high temperature. Hydrothermal synthesis method is widely used to prepare carbon quantum dots from green materials such as ginger, beef meat, milk, and in this case we are using orange juice. I need to close the lid tightly with the locking rod before it goes into the furnace. Okay, now we are at the furnace. Let's place this in there for 8 hours. I will set the temperature to 180 degrees and set a timer. See you in 8 hours. Okay, now that 8 hours is up, I will go ahead and take the autoclave reactor out. I need to use thick gloves because the stainless steel shell of the reactor is very hot. We will leave it here to cool. 2-3 hours should be enough. See you soon. Okay, now we are at the workbench again. The autoclave reactor is cool to touch. Now I will open it up. Now we need to purify the solution in the reactor. The purification should be done as there might be some unreacted or overreacted particles or even some contamination in the solution. I open a syringe and suck up the solution in the Teflon. I think you can also notice that the solution color has been changed from yellow color to brownish color. Then I attach a 0.22 micrometer filter and push the sample through it with the plunger into the plastic flask over here. It has a volume of 50 milliliter. That should be enough to hold most of our sample. So as you can see, this filter will help us to remove the contamination and the unwanted particles from our solution containing carbon quantum dots. There we have it, pure carbon quantum dots. Now you can view them under a UV lamp and see how they fluoresce. This is how they look like under normal white light. And then I have used the UV lamp to see what the carbon quantum dots will do when I expose them to UV light. Wow! You can see now they are shiny and glow like a star. So now we can see just how tiny these nanoparticles are. I'm going to use transmission electron microscopy or TEM as a super powerful instrument to measure the particle size of my carbon quantum dots. TEM is a microscopy technique in which a beam of electron is transmitted through a specimen to form an image. First, we prepare the TEM grids by dipping the grid to the synthesized carbon quantum dot solution. We will leave it to dry for a couple of hours in the dark and room temperature. Now we have our sample ready. Now the grid will be transferred to the TEM sample holder. A TEM grid is typically a flat disk with a mesh or other shaped holes used to support the particles. The holes in the grids allow the electrons to pass through. Grids are available in wide variety of patterns and materials for various applications. Grids are available in different types of materials as some specimens will react with certain materials and some require analysis at higher temperature. TEM grid can be made from copper, molybdenum, nickel, gold, titanium, stainless steel, and aluminum. Then the sample is placed in the TEM machine and we wait to pump down and achieve the proper pressure and vacuum. We need to fill the sample holder with liquid nitrogen, which help minimize contamination and improve the vacuum and recovery time from specimen insertion. Also, freezing the samples prevents them from evaporating in the vacuum of the electron microscope. In addition, the low temperature will also protect the sample from damaging interactions with electrons used to image the sample. Now we are turning on the filament to generate the beam and expose to the sample. It takes a minute to warm up. Then we need to align the beam on our sample, which makes us able to see our particles very clearly. Sometimes this can take a long time. Now you can see how our carbon quantum dots look like under the microscope. These dots are amorphous and round-shaped with a particle size in the range of 2 to 10 nanometer. You might be wondering if there is a chance to change the particle size of the carbon quantum dots. I should say yes, it is possible. We can change the synthesis parameters to achieve two particles with different sizes. For example, to achieve particles with bigger size, we can increase the reaction time and the temperature of the furnace during the synthesis of the carbon quantum dots. Or here, I have used 3 filters with different sizes to separate the synthesized carbon quantum dots based on the particle size. You can see when I use a filter with small pore sizes, I could achieve particles with the average size of 2.3 nanometers. And then by using a filter with larger pore sizes, I could obtain carbon quantum dots with particle size of 4.2 nanometer. Also, the fast Fourier transform or FFT show no diffraction, which also shows that these dots are non-crystalline in their structure.